Hello, my people. Hope you're doing well. We're going to go ahead and get started on some practice problems for this subunit of right triangle trigonometry. And the instructions that are given for this particular problem is use the given function values and trigonometric identities, including cofunction identities, to find the indicated trigonometric functions. Okay, so we know that 30 degrees is a unit circle value. So, we could find these values very, very easily, right? Just by, sketching out sort of first quadrant stuff. Not an artist. Okay, and that right there, it's 30 degrees, and we know that that has an ordered pair of root 3 over 2, 1/2, right? And so we could use that, and go ahead and turn into a triangle and give me the sides. That's root 3 over 2, and that's 1/2, and that's 1, and all sorts of fun stuff like that. But what we're going to do instead is we're going to use trigonometric identities, and I'm going to show you that these identities are basically reveal necessary relationships between the trigonometric functions. These things have to be true, not just at some particular value, but at every value of theta. And we're going to go ahead and see how that works. Now, in part A, we're asked for the cosecant of 30 degrees. Now, we know that by reciprocal identity, that cosecant of theta is equal to 1 over sine theta. That means that this is 1 over sine of 30 degrees. Well, sine of 30 degrees, we already have right up here. It's 1/2. So you have 1 over 1/2 or 2. Okay? And we didn't, we could have used the cosecant ratio of hypotenuse over opposite, but we didn't. We used instead the identity to find that. Now, that one is really, really simple and pretty straightforward. We go, okay, well, this is going to be easy. Well, they do get a little more complicated. And we see cotangent of 60 degrees. Okay? Well, we happen to know that cotangent of theta is equal to tangent of 90 degrees minus theta. That means if theta right here is 60 degrees, 90 minus theta is tangent of 30 degrees, and that we already have told to us explicitly in the given, and it winds up being root 3 over 3. Now, again, we could have gone over to our triangle and recognized the fact that this was 60 degrees, and we could have used our cotangent ratio of adjacent over opposite, put 1/2 over root 3 over 2, and basically, worked it out until we found root 3 over 3. But we didn't. We actually used the cofunction identity instead. Okay? Now, the next one, we're going to go ahead and skip C because I'm going to do it on a separate sheet of paper. Let's go ahead and do part D. Part D is the cotangent of 30 degrees. Well, cotangent of 30 degrees, we know that cotangent of theta is equal to 1 over tangent of theta. So that means, that means that cotangent 30 degrees is 1 over tangent of 30 degrees. And that means it's 1 over root 3 over 3. Or if you actually remember the fact that this root 3 over 3 represents something that was rationalized, you get root 3. And we could have, again, used our cotangent ratio for 30 degrees, but instead we used a reciprocal identity. Now, what we're going to do now is we're going to do cosine of 30 degrees, and we're going to do it two different ways. Okay? Sine of 30 degrees in our problem was equal to 1/2. Tangent of 30 degrees was equal to √3/3. And in part C, I'm asked for the cosine of 30 degrees. Now, there are two ways that I can do this. The first is to recognize that tangent of theta is equal to sine theta over cosine theta, which means that, if you sort of switch it around and solve for cosine, you get cosine of theta is equal to sine theta over tangent theta. And if we use this, then we simply have to take these two values and plop one over the other. But I also remember that sine squared theta plus cosine squared theta is equal to 1. That's going to be a fun one. Let's do this one first, though. I recognize that cosine of 30 degrees is equal to sine of 30 degrees over tangent of 30 degrees, which means that this winds up being 1/2 over √3/3. And that's going to be 1/2 times 3 over √3, or like I said in the last one, you need to remember that this was actually that √3/3 was originally 1 over √3, and the denominator has been rationalized. So if you just remember that, then basically you get cosine of 30 degrees is equal to √3/2. And of course we could have gotten that just by remembering our unit circle values, but what would be the fun in that? Okay, we instead used these identities to determine the value. Okay, now I can't stress this enough, and I'm going to say it like a broken record over and over and over again. Identities are not like equations. Equations are things that we solve, and we are asking for what value of the variable is this true. Identities such as these are true for every value of the variable, and in that way they are distinct. Okay, and we need to basically remember that some equations are questions, and some equal signs are questions, like when they're an equation and we're asking to solve. Some equal signs are statements of fact, like sine squared theta plus cosine squared theta is equal to 1 for every value of theta ever, 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 off until the end of the world. Okay, and so, it doesn't matter whether it's cosine of 30 degrees or whether it's cosine of 517 degrees. It's going to be the same. So what we need here is sine of 30 degrees squared plus cosine of 30 degrees squared is equal to 1. All I've done is taken this and basically plugged in a particular value of theta rather than just leaving it as any old value of theta. Okay? Now, sine of 30 degrees, we have a value already. That is 1/2. Okay? Cosine of 30 degrees is the thing that we are trying to evaluate, because we're gonna pretend like we don't know this right here. Okay? Like I said, I want to do it more than one way. Now, 1/2 squared is 1/4. Okay? And we get cosine of 30 degrees, sorry, that's terrible right there. 30 degrees squared is equal to 1, or cosine of 30 degrees squared is equal to 3/4 when I subtract 1/4 from both sides. Now, when I take the square root of both sides, in most instances, I would do the plus or minus, but the fact that it's 30 degrees and I know it's in the first quadrant answers that question for me. It's the positive one, and therefore it is root 3 over 2. Okay, and I arrived at that by using two different identities. Yay me. Okay, let's go ahead and look at a value that is a little bit more, it's not a unit circle value, so that's going to be a little bit more tricky. But let's go ahead and dive right in. It's the same instructions as before, and we see here that cosine of beta is equal to root 7 over 4. Now, I recognize that secant of beta is equal to 1 over cosine of beta, and that means that it's 1 over root 7 over 4, or 4 over root 7. Now, this is going to be one of those things, you know how you were always told to rationalize the denominator? I'll explain to you at another time why you were asked to do that. That's actually, there are some varieties of simplification that are basically going to go right out the window in this next year, okay? But for the sake of just, you know, continuity with what we've done before, let's call it 4 root 7 over 7, okay? Rationalize the denominator by multiplying by root 7 over root 7, and there we go. Now, B, we're being asked for sine of beta, okay? Well, let's go ahead and do that same thing that we did in the last one and say sine squared beta plus cosine squared beta is equal to 1. Well, sine squared beta is equal to 1 minus cosine squared beta, and we can go ahead and plug in for that cosine squared beta. And now remember that this can also be expressed as this, right? If we sort of unsimplify, right? Because the bottom, like 4 is the square root of 16, and then we can sort of like reverse the properties of the rules of exponents or rules of radicals, right? And so basically, if I were to square that, I would get 7/16. Okay, well, let's go ahead so we don't get too far down the piece of paper and start over here in another column. I'm going to get sine squared beta is equal to, well, that's 16 over 16 minus 7 over 16, so that's going to be 9/16. Okay, and therefore I'm going to get sine of beta is equal to plus or minus 3/4. The reason that I have the plus or minus is there is some ambiguity as to which one it is, because cosine, if you remember, is positive in 2 different quadrants. And if there is no indication as to which quadrant you're in, then you have to account for both, right? Cosine right here, root 7 is, gosh, I mean, if root 4 is 2 and root 9 is 3, then root 7 is probably 2.6 or something like that. So it's between 1/2 and 3/4, okay? And that is true. Remember the unit circle, okay? Remember the unit circle. Let's see if I can actually do an okay unit circle. Oh, that's better than I do most of the time. Okay, and if we're looking for where cosine is between 1/2 and 3/4, right, it's going to be right about here, okay? Well, that is true for 2 different angles. The angle measurement that terminates at that point on the unit circle and the one that terminates at that point on the unit circle. And those basically are, you know, this one right here is root 7 over 4 3/4, and of course this is not to scale. Root 7 over 4 negative 3/4, correct? And if in the question you are not given an indication as to which one it is, you have to go ahead and account for both. I think I've pretty much driven the point home on this. So I think we can go ahead and move on to the next problem. But problems like this, we'll do another one during the lecture, and that'll sort of firm us up in terms of our understanding of that. Now the next question, the next variety, and basically what they're going to do in this section is they're going to come at these concepts in a variety of different ways, because that forces you to sort of look at these concepts from a bunch of different perspectives. Now, use the Pythagorean theorem to find the length of the missing side of each right triangle. Then find the value of each of the 6 trigonometric functions of theta. Now, notice that 10 and 26 have a common factor, okay? This right here is 13 times 2, and this right here is 5 times 2. Now, if you remember your Pythagorean triples, you remember the fact that there's a 3, 4, 5 right triangle, but there's also a 5, 12, 13 right triangle, which means that this side has to be 12 times 2, or 24. But let's say you didn't recognize that. You can still figure it out, okay? And what happens here is you have 10 squared plus, and we'll call it x squared, is equal to 26 squared. Now, 10 squared, that's pretty easy. But this winds up being 676. By the way, one of the things I need you to memorize is all the perfect squares up to 30 squared, because if you don't know them and you can't recognize them, I'll also teach you a trick on how to find them if you ever forget one of them. But for our purposes right now, this winds up being x squared is equal to 576, and x is equal to 24. Okay. Now, I have all 3 sides. Now I can fill out all of these, okay? If this is my theta, opposite over hypotenuse is 10 over 26, but of course, the 2's will cancel out in any of those ratios, and I'm going to get 5 over 13. And of course, its reciprocal is 13 over 5. Cosine is going to be adjacent over hypotenuse. That's going to be 24 over 26, or 12 over 13. And of course, the reciprocal is 13 over 12. Now, the tangent is going to be opposite over adjacent. It's going to be 10 over 24, which reduces to 5 over 12. And that, of course, has a reciprocal of 12/5. Okay. Now, that... let's go ahead and talk about Pythagorean triples before we finish out this video, and then we'll sort of jump in with another type of problem in the next video. Now, Pythagorean triples are based upon, basically they are when you get integer solutions to x squared plus y squared is equal to z squared. Okay? And there's actually a formula for them. I'm not going to share that with you right now. It really doesn't. I mean, it's not going to be helpful to you. It's kind of neat, but it's not going to be helpful for you. But you need to remember that when you square things, there's a progression, okay? 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared, 5 squared, 6 squared, 7 squared, 8 squared, 64, 9 squared, and 10 squared. Now, what you need to recognize is that as it goes along, the difference between these is 3. The difference between these is 5. The difference between these is 7. Oh my gosh, I see a pattern. The difference between these is 9, and there is your 3, 4, 5 right triangle. The difference between these is 11 and 13 and 15 and 17 and 19. And then we'll start over with 100 again. So that's 10 squared and 11 squared and 12 squared and 13 squared and 14 squared. Difference between these is 21. Difference between these is 23. Difference between these is 25. Oh my gosh, there's your 5, 12, 13 right triangle. So basically, for our purposes right now, you can think of the Pythagorean triples as when two squares have a difference that's also a square, okay? And that's also true right here in the 7, 24, 25 right triangle, because 24 squared, as we've shown, is 576. 25 squared is 625, and the difference between those is 49. Guess what the difference between 40 squared and 41 squared is? It's 81, because 40 squared is 1600. Okay? 41 squared is 1681. Okay? And if you're thinking to yourself, gosh, 41 squared, remember that that's 40 plus 1 squared, and we can just FOIL it. 1600 plus 40 plus 40 plus 1 is 1681. And there you go. Okay? So, I hope that gives you a little bit of insight into Pythagorean triples and how they're related to the way that perfect squares progress in a sequence. Okay? We'll go ahead and call an end to this particular video. We may have 2 more videos. We may actually, we'll probably just have 1 more video. I got a couple more problems. Need to do a couple of word problems and sort of show how these principles actually are applicable in real life. Not that that's necessarily makes math worth more when it's applicable. Sometimes the non-applicable math is the most fun. But these actually do have real-world implications in terms of like angle of elevation, angle of decline, all that sort of fun stuff. But I'll save that for the next video. Bye.